Welcome to the December meeting of the Hamilton Amateur Astronomers. For those that don't know me, I'm John Govro. I'm currently the chair of this most excellent club. We have a great meeting in store for you tonight. We have a very special guest speaker. We have some special prizes for later on. Just right off the bat, I'm just going to mention a couple of things. A reminder to anyone who ordered a calendar in the second print run that they are ready. If you arranged for pickup, the pickup is tomorrow, and you received an email today about that. If you didn't, then you can get in touch with me directly afterwards or tomorrow. I want to offer a thank you to Steve Germain for doing a great job with the Observer's Handbooks, which have been, almost all have been distributed now out into the hands of some very happy recipients. I'll also mention that it's wonderful that all of you are able to join us online like this. We certainly miss meeting in person, and as all of you know, every month when we meet, we do take up a donation, a collection for the local food bank. Because we're not meeting in person, we can't do that, but I still encourage all of you to make contributions on your own if you were at all able to do so. They're every month it is appreciated, and I'm sure this month more than most. So with those announcements out of the way, I would like to hand the floor over to our guest speaker and get on with the good stuff, the good part of the meeting. Our guest speaker tonight is Dr. Yanqin Wu. Dr. Wu took her PhD at Caltech and is now a professor of theoretical astrophysics at the University of Toronto. Her current research interests centers on planets in our solar system and beyond. She studies their internal structure, their dynamics, how they form in their protoplanetary disks. And over the past few years, she's been, in her words, staring at the planets discovered by the Kepler space mission, looking for clues to their formation and evolution. And I'm very much looking forward to her presentation tonight. I know that I speak for all of us in offering a warm welcome to you, Dr. Wu.
Oh, thank you. Thank you. Thanks, John, for such a nice opening. Actually, I must say I have respect for all of you. As I said, to spend a cold Friday evening sitting in front of a computer listening to a science talk. I wish my kids have the same sort of enthusiasm for science. I'll see how they turn out. Okay, so I'm going to start sharing screen. Let's see if I can do that. I prepare a small talk, just 10 slides, because even though we're sort of doing it over the computer, I like to make it as informal as possible. What I would like to do is just sort of tell a little story about this Earth 2.0. I'm sure you know what it means. It means finding other planets, which is exactly like Earth in the sense that going around a star like the sun, not too hot, not too cold, and at just about the right distance from the star so that there is chance that life could survive or life could start and then prosper on the rocky surface of that planet. That's what we call Earth 2.0. We are very far away from finding life on this kind of extrasolar planet, but I think we are probably not that far away from finding this kind of planet. That's why I say it's a hunt, it's an ongoing hunt, and we're probably going to succeed in the next couple of years. So that's the story I want to tell. Can you see the whole screen or something blocking it?
No, it's coming through very well.
Okay, nothing is blocking the screen. Okay, good. Okay, I'm not sure how this name, the Kepler space mission, is probably in the news a lot, but I'm not sure everybody's familiar with it. If it's not, and then just bear with me like 1 minute or 2 minutes. I give a very, very short introduction of this mission. This is a mission that has, as I said, I've been staring at a planet discovered by this mission. And it's been my last 5 to 10 years of, maybe 5 years, my scientific journey has been using data from this particular mission. And around the world, there are lots of other astronomers who've been doing similar things as I do. We've been learning so much from what this space mission come from. This one's actually a fairly large telescope. I think the diameter is something like, we use centimeter in astronomy. So 95 centimeter with something like a 40 inch telescope. So it's fairly massive telescope. It was sent up by NASA 2009. So by now more than 10 years. It stayed up operating for 5 years, mostly 4 years. And then afterwards, it got pretty much shut down. That's kind of a sad story. I'm going to talk about why did it get shut down later. So really, it has a proper working life of about 4 years. Over that 4 years, it provide a huge amount of information. I'm actually not mostly going to talk about that, even though that's really fascinating too. I'm mostly going to talk about what Kepler failed to do. So this is what it failed to do. It was designed with this one single purpose, which is finding Earth-like planets around other stars, because NASA and probably a large proportion of the public, we all want to know whether there are life out there. And if you want to find life, the first solid step, so first concrete step, is to find planets that life can live on. So that's where astronomers' one central goal now is to find such planets around other stars. So Kepler was designed with exactly this purpose. And the strategy was incredibly simple. You're going to stare at that patch of the sky. You see those little squares. So that's each one CCD of a Kepler is going to be responsible for. And it's going to be staring there unblinkingly, unmovingly for 4 straight years. No change in what Kepler doesn't care about every other part of the sky, doesn't care about whatever exciting thing happened, but only just faithfully staring at that patch for 4 straight years. And it thought that, well, this is a tiny patch of the sky. I'm sure you're all familiar with the Milky Ways and all these, all kind of nebulas around here or not. This is sort of a generic patch of the sky. There are lots of stars in this patch, bright enough. I'm sure some of them you may even taken pictures of it. But Kepler is only responsible for monitoring something like 200,000 stars in that field. Because those 200,000 stars, he believes, is the best candidate to find such Earth-like planet. And the detection method is very easy, right? If one of those stars have planets going around it, by luck, some of those planets will be going in front of the star from our point of view, and we will be able to see the star get a little bit dimmer or transit. So that's a really simple philosophy. And after 4 years, as I said, it's a bit of a failure story, so I'll tell what the failure is about, okay? This is the same thing I was saying before. It will be staring at lots of stars and hopefully to be seeing one small little potato, in this case, a black dot like the Earth, going in front of the star, so part of the starlight is going to be covered. You will see that if I take flux measurement, brightness measurement of the star, it will suddenly go a little bit lower for about 13 hours every year. So half a day every year, this is going to happen. This is why Kepler has to be faithfully staring at the stars, can't blink, right? And then it go back. So this is what it wants to find. This is a very difficult measurement. Why is it very, very difficult? Earth is so tiny compared to the sun that when Earth goes in front of the sun only dims by about part in 12,000. It still sounds pretty good, part in 12,000, but actually the star is actually kind of noisy. As you can see, the stars, each blue point is one of the stars flux measured at different times. The star is jumping around because the star is not perfectly constant. There's all kinds of activities on top. So to see those you actually need the precision much better than part in 12,000. I'm going to talk about precision a bit later. Okay, so this is the simple single equation Kepler was banking on. This is how so when it convinced NASA to launch such a mission, this is the sort of key equation Kepler put out there and saying, look, we're going to succeed. Why? It says we're going to be able to find this many Earths. And to find this many Earths, how do we calculate that? Let's say we're going to stare at a certain number of stars. Here, I want to include the really good stars. So about 12,000 good stars in Kepler's field. Okay, that's a number of good stars. And if every star has one Earth orbiting around it, so we don't know that number. This is in astronomy, it's called the eta Earth. It's a very fashionable term. Everybody's going after. It's a term that's also appeared in the so-called Drake equation. Okay, so which is that how often do stars have Earth-like planet? Before Kepler go up, we have no idea. So let's set it to be 1. So every star has 1 planet. This is a big number. This is actually a very small number here. This number is saying this planet has to have an orbit just right for us to see the transit, because the angle, if it's the orbit is not perfectly going in front of the star, we won't be able to see any dimming. So this is called the transit probability. In the case of Earth going in front of the sun, it's about 0.200. So if you are alien sitting somewhere in the sky, depend the way you are on the sky, some alien can see us going in front of the star, in front of the sun. Some aliens cannot. It's about 0.200 of the aliens can see it. Okay, so that's the transit probability. So very simple. 12,000 good stars. This number is 1. This number is 1 over 200. You can even do it in your mind. Kepler says we're going to find 60 Earths. That's going to be amazing. So NASA agreed. Let's send up $1 billion mission and let's go find 60 Earths. Remember, this is before we didn't know any other Earths. So from 0 to 60 is a huge step. So let's go. Kepler was launched 2009. Now it's 2020, so 11 years later. We now have done lots of work, lots of statistics, lots of digging, lots of corrections, lots of verifications. We found 0 Earths. So I would just want to use 1 or 2 slides to explain why the Kepler failed. Okay, so this is the same number, same formula I was showing you before. How many good stars you're staring at, how likely planet exists, and what's the transit probability. This one can't change. This one just geometry. So these 2 numbers, both numbers can change. This in particular is not very certain how common Earth is. This number turned out was really problematic for Kepler. What do I mean by that? Okay, this is a little bit more detailed picture. On the horizontal axis is magnitude of stars. So the stars Kepler was staring at, they're not visible by eye. There are not enough visible stars on the sky in that patch. So they're looking at 10th magnitude stars or even down to 16 magnitude stars. So between 10 to 16 magnitude, there are lots of those stars out there. But really, only really bright stars in that range are good enough for Kepler to take a picture to measure how bright it is and look for transit, right? So as you can see here, there's a vertical axis. I'm not going to explain what it is, but roughly it's just how bad we can measure light. If it's very small, very low down here, that means we can measure the light very, very precisely. And that makes it easier to see the transit, to see the dip. This up there, if you go up, that means measurement error is very large. In particular, so it makes sense, right? Very bright stars. So very bright stars can have very small measurement errors because they're very bright, lots of photons. We can do it very, very precisely. But very dim stars gets harder and harder to measure the light very precisely. And before Kepler went up, it did this estimate. So everything in this blue box, cyan box, is what I call good stars. Everything in this cyan box will be precise enough measured by Kepler that we should be able to see Earth. That's why the estimate of 60. I'm going to show you how this diagram, same picture looks like after Kepler's gone up. Something changed. Okay, so it's the same axis and so on. That you can still sort of see the same trend as I showed before. Dimmer stars we can't do as well. We don't measure precisely enough to measure the dip. And brighter stars we do a little bit better. Precision is getting better and better. Those we should be able to potentially measure Earth. But see here, there's all the stars here. Some of the stars are really, really bright. But for some reason, Kepler couldn't measure the light precisely. The errors are very large. Because of that, if you count all the stars in the cyan boxes, instead of 12,000 stars, we now cut down dramatically to only 2,000 good stars. That's really sad because right away, the number of Earths you could potentially get gone down factor of almost, not quite 10, almost 5, okay? You still expect, okay, even if I go down by 5, I should still be able to see 10 Earth. Kepler found 0. Why? That's the second bad luck. Turns out Earth is not that common in the universe. We now have a sort of upper constraint on this eta Earth magic number, which is that, as I said, naively, we expect every star to be having an Earth. The sun is not special at all. But now it looks like the sun is somewhat special. Only 1 in 10 stars probably has an Earth. Okay, at this point, maybe it's good to ask any audience, any comments or questions or clarifications, or feel free to ask.
If anyone wants to ask, they can put up their hand and I'll moderate the questions, or you can put your question in the chat if you would like.
Yeah, just, yeah, I don't mind anybody barging in. It's actually good. I want to be more informal. And so bottom line of this is that Kepler did not find any Earth because 2 things. First is that these points, instead of lying down here, they jumped up. Star somehow it's very difficult to measure those, even bright stars, very difficult to measure their photometric brightness. The other thing is that the sun is somewhat special. We belong kind of the 10% rareness in the universe to have Earth. Okay, that's very disappointing. I just want to say just one word about why the stars jump from suddenly a promise of very good precision measurement suddenly jump to here, which means very lousy measurement. And that's what we're showing here, right? This is a typical star in that part. If you see its brightness keeps on fluctuating continuously. While some stars down here, the brightness actually is very constant or nearly constant. If it's nearly constant, you can see the dip really makes a difference, right? But here, a dip, like I actually drew a dip there, but you can't see. The star is so noisy. So the question is, why is it so noisy? What's causing by? If you see the little picture I have up here of this, so a picture of the sun, you can see very well. A picture of the sun up there, you can see the sun's surface is actually not a monolithic bright disk. The sun's surface is actually full of spots, full of brightness regions, full of what we call turbulence, convection cells, buoyancy cells, all kinds of things. The sun is really just a big bubbling hot pot. And as a result, photons from the sun will carry that information and keeps on fluctuating and give us really lousy flux measurements. It makes it very hard to detect Earth. So that's really Kepler's big surprise, is that lots of stars are like that. Lots of stars are not quiet, very noisy.
Dr. Wu, we have a couple of questions in the chat.
Yeah, please just go ahead. And you can also just talk to me. Yeah.
Okay,
yeah.
I'll read you the question. This is from Andrew. And Dr. Wu, do you think with improved technology, i.e. telescopes, that we will find more Earth-like planets?
Right, okay. So one thing naively think is that, okay, why don't we send a bigger telescope Kepler is about, as I said, 95 centimeter diameter. What if we send a 5-meter diameter or even 10-meter diameter? Let me be ambitious. It turns out it wouldn't help at all. Why? Because this precision, this kind of errors on the measurement is not because we don't have enough photons from the star. It's not because our telescope's not good enough. It's because the stars themselves are very noisy. So unfortunately, no, doesn't help.
Okay, I have a second. Oh, sorry.
Yeah, I don't know if that answers the question, or if that's the question.
I have a second question for you. Andrew can get back to me if you want.
Mm-hmm.
This is from Matthew. So are the large planets in the early system formation displacing or consuming the smaller rocky planets?
Yeah. So is it possible? So that's the next question, right? Why is Earth so rare, less than 10%? Is it because, for example, maybe they were formed very popularly, very commonly, but then somehow consumed by other bigger planets, like you suggested, or they collided with each other and destroyed each other, or we don't know. It would be nice to first, actually we have some early, there's a different story. We actually have some early suggestions. We made some claims. We suggested that there are actually some planetary systems which have undergone huge havoc, where the planet have indeed undergone a lot of collisions, and perhaps they reduce somewhat, but reduce it from 100% to 10%. I don't know if that's possible. And I would actually at the moment think may have something to do with that forming Earth is not that easy a process.
We have a couple of questions from our YouTube viewers. This one is from James White. I thought Kepler had found an exoplanet containing liquid water, or was that science fiction? Kepler 22b.
Okay, so I do not know. So there are Kepler, I haven't talked about it, but Kepler found about 5,000 extrasolar planets. And many of them are giant planets like Jupiter. So they contain water in there, but in the form of vapor. But I don't think you mean that. You meant the ones which are smaller and probably are more Earth-like. This we call super Earth. I can explain why I don't consider them as Earth, but these are called super Earth. And people have been trying to see, for example, like you said, whether they have ocean on the surface of this planet. All I've heard now is that we have not found ocean, and it makes perfect sense because those super Earths that Kepler found, they're all very close to the star. Earth is going around the sun at some large distances. We go around very slowly once a year, but those super Earths goes around once every 10 days, so very close to the star. The surface temperature is about maybe 1,000 degrees. Or probably even hotter. So vast majority of them don't have any chance for liquid ocean. And that's also why they're not that exciting for life. I'll look up Kepler 22, just make sure I'm correct, yeah.
Dr. Wu, we have a few more questions. Do you want to take them now, or do you want to hold them and continue with your presentation?
What do people usually prefer? I'm okay either way.
Okay, then we'll continue with the questions since these people asked them. This is from Bernie Vanass. Do the potential Earths include a tidally locked moon?
Right. That's a very interesting question because tidally heated moon could potentially host life. So even if you're not like Earth going around at the right distance, you can actually go around another planet and be heated by the tides. So that has been suggested for example, for Europa, one of Jupiter's moon, and Enceladus, Saturn's moon. And it has been suggested they could also host life. Possible. They could host underground life because whatever ocean they get, because the tidal heating is under a layer of ice. And NASA is sending, at the current moment, is going to send some missions to drill in those thick ice shells and to check if there is any life there. We don't know yet. So it's potentially possible you can have different kind of life, which is not like the Earth.
We have a question from Dan Creek. What about moons or planets with subsurface oceans?
Yeah, I think that belongs to this last question. Yeah. So all the planets Kepler's found today, as I said, all the super Earths are too hot. So even silicate is starting to melt near the surface, some of them. So if they do have a very thick crust, it will be silicate crust, which is a little bit hard to have ocean under that. But if there are moons around other planets, but at large distances, they could have underground ocean and they could have life. That is a big unknown.
We have a number of questions. I'm going to do one more and then let you continue with your presentation, and then we'll come back to a couple of the others that have shown up. Is that okay? I'll give you one more for now.
Yeah, thank you. Yeah, sure.
This is from Doug Curry. How much is the limited observation per star by Kepler responsible for the lower than estimated discovery of Earth-like planets, especially around more solar mass stars?
That's such a key question. Okay, I'm going to just get to that. So should I just go on? Because I'm going to get to that.
Go on with your presentation, and then we'll do a few more questions a little bit further on in your presentation.
Yeah, okay, great question. Okay, so the question is that what about extend Kepler observation for a few more years? And maybe there are Earth-like planets. You just need to listen to the star and keep on collecting data. At some point, you're going to find the Earth. Actually, I think that's very likely. In particular, for example, I just took this one as an example. In this particular case, this is the light curve. You can see the luminosity of the star. There is a potential dip here. In this case, if it is a real dip, this could be an Earth-like planet at 400 days period, so almost a year period. So this is a potential Earth candidate discovered by Kepler, but Kepler cannot claim it as a discovery. Why? Kepler only seen this planet, if it is a planet, have only seen it dipping for 4 times or 3 times. And as a result, the noise just a little bit too much for us to be confident that this is really a planet, rather than there are all kind of instrumental effect. Guys, people like you who deal with telescope knows that there's a huge number of things that could go wrong. So this moment, this one is considered a candidate, but not even close to be accepted as a real detection. So that's what I said in this title. This is a candidate, this potential candidate hiding in the data. So really what we like to do is that you would like to keep Kepler on the sky for another 4 years. After 4 years, you're going to see the 4 more times, you fold it up together, you will know for sure. Kepler was going to do that. I don't know if you have or have not heard of this painful word, co-reaction views. Kepler was I think it's almost $1 billion spaceship. Really expensive, took many years to build. It's beautiful, working spectacularly well, much better than people have expected, except for one part of it. And that part is called the reaction view. In fact, this very important part is the part which is almost like a top. It's like a spinning top. It's the part that keeps the telescope fixed at one direction in the sky. If it's not because of these reaction views, Kepler will keep on tumbling, will go around looking at different parts of the sky, and that's going to make it very hard to measure the stars. And at about 4 years end, at the end of the 4-year mission, Kepler was saying, we want to go on another 4 years, but the reaction wheels failed. We actually did a very careful study on why the reaction wheels failed. It's very interesting, but I'm not going to have time to go into it. So that's the sort of the cautionary tale. It's a $1 billion mission, failed because of part which only cost $50,000. That's a real pity. What I show here, this is just something I grabbed online. You can see Kepler mission is here. As you can see that this is endeavor, human endeavor, which is not going to stop at Kepler. there's actually quite a few missions that's already planned. In fact, TESS is already on the sky now. JWST is already soon going to be launched. WFIRST is soon going to be launched. All these future telescopes are actually not only just planned, many of them are already soon to be in operation. And the purpose of many of the space missions was to study Earth, but Kepler didn't find them. So what are they going to study? So it's a serious problem at the moment. It's a very pity that the reaction whales disaster happened. This is actually a little bit of our own research. I don't know how much time do I have in terms of my presentation?
That is entirely up to you. You take whatever time you like, and when you feel you're done, then you say so. It's up to you completely.
Oh, that's very generous. Okay, well, let me explain this by explain this is actually a paper we just submitted last Monday. It's a paper that's a research of one of my undergraduate students, actually really a brilliant undergraduate student. I want to use this to motivate that Earth is actually probably, we're starting to see some evidence of Earth. Okay, so what I show here is, again, it's a different kind of graph from what I showed before. So this is the so-called radius of the planet. So every blue point you can see here, I don't know if you can see 4,000 blue points. There should be 4,000 of them, about 4,000 of them. Every blue point is a planet discovered by Kepler. This is the size. We use radius. So 1 means same size of the Earth. 2 means twice as big as the Earth. So if it's twice as big as the Earth, that means, you know, it's actually mass-wise, its mass is almost like 10 Earth mass, 10 times the Earth, 10 times the mass of the Earth. That's why we call them super Earth. Okay. On the horizontal axis is the distance away from the star. So this is 1 day. That's crazy, right? The planet's going around the sun once a day. This is 10 day, 100 day, and Earth is sitting about 365 days, 1 year. So that's why I put a little Earth stamp here. You can see that vast majority of the planet that Kepler discovered, all these blue dots, are sitting very close to the star. And that makes sense because it's easier to find them. They transit much more, they're much more likely to transit. And vast majority of them are either called super Earth, that's these things, or called mini Neptune. They call it mini Neptune because Neptune had the size about four times Earth's radii. So this is smaller than Earth. That's why it's called, smaller than Neptune. That's quite they call it mini Neptunes. We actually been doing a lot of work on these mini Neptunes and super Earths and trying to understand what they are. Are they water planets? Are they made of hydrogen? Are they made of rock, iron, and so on? And where did they come from? But I'm not going to talk about those. So this kind of planets, unfortunately, we come to the conclusion that they are not suitable for life. Okay, that's kind of it's going to be a long story, so I'm not going to go into it. Somebody can ask later on why they are not suitable for life. But we are really interested, we're really interested in planets that have solid surfaces and does not belong to this two clump, this sort of bigger planets, kind of brutes in schools. So we're really interested in smaller planets which are distinct from these bigger planets. And as I said, this paper we just published showed that there are such small planets. So we actually, we look at planet in this green box and we plotted out how many planets at every side. These are the super Earths and mini Neptunes. They're bigger than Earth, right? And there are lots of them. The universe seems to be filled with them. We now find out about almost half the stars have those kind of planets. They're much more common than the Earth. Okay, and then we realized that after a lot of work, we realized that the super Earths and mini Neptunes, they actually become rarer and rarer as you go towards the size of the Earth. Another way to say this is really a different beast. How they formed is going to be very different how the Earth is formed. So, and they're unlikely to have life on them. They're going to keep on decaying until we go smaller than Earth. It turned out Kepler just found a smattering of small planets smaller than Earth. We call them sub-Earth, sub-Earth. We found out that this is interesting. Okay, the most interesting thing is that it keeps on dropping, but then the number picked up again around Earth's size, and then keeps on rising. Oh, sorry, keeps on rising, but we short of data here, so there's no more data. So it looks like there's a new group of planets which coming right at the sides below the Earth. We call them sub-Earth, and we think these are Earth analog. What do I mean by Earth analog? We're looking at really hot areas, very close to stars. We're not even close to the Earth, but we're seeing some population which may be solid surface like the Earth is. And we just hope that this population, this sub-Earth population, continues filling all this space, filling all the way to the position of the Earth. So this paper is currently under review, but I've been hearing a lot of response about it, so people are getting excited. Okay, so this is my last two view graph. Okay, I brought kind of a disappointing news saying that Kepler found 0 Earth, but then I also show that there is sort of tantalizing evidence that Earth, or at least Earth analog, seem to be quite common. Well, Earth analog seem quite common. How common Earth is not quite well known. What do? We have to send out more missions. We need more data. So here on the left-hand side, I show two little insects. That's why I said I'm working with much smaller telescopes than you guys have. This one is actually not the mission I'm involved in. This mission is called Plato. Beautiful name. It's by the European Space Agency. It's going to be launched in 6 years' time. See how it's made up? So if you count the numbers here, it's about 26 little telescopes. Each one of them is about 12 inch. And they're going to put such did I calculate right? Each one of them 150 millimeter. 150 millimeter is, no, less than 12 inch. More like a 7 inch. So tiny. Each one of them is tiny. So they're going to send up this as a big mission because there are many of them, even though each one of them is very tiny, and going to pretty much do what Kepler does, staring at a piece of the sky and hopefully make up for what Kepler could not do. The lower one's the one I'm actually very engaged with. I'm kind of a science PI for this mission. We call this mission, at the moment, we don't have a good name for it. So I'm welcome any beautiful names that has good synonyms and has a good meaning and sounds well. For the moment, we just call them Earth 2 mission. And this one's a little bit different. Design philosophy and strategy is very different from the Plato mission. It doesn't sound very different, but actually bottom line is very, very different. So instead of having 26 tiny telescopes, we have 7 telescopes. And each one of them is a 30 centimeter, 12 inch telescope. And I've been doing lots of predictions for how many Earths should we find using this Earth mission, Earth 2.0 mission. Oh, by the way, this is currently funded by the Chinese Space Agency. China's been very ambitious. You know, you may have heard, we just have a mission landed on the moon, collected moon rock, and is on its way back. So China's been very aggressively pushing for space mission, but this one is a science mission, and I think it's a good idea to go for it. So we, for example, depending on, for example, in here is our prediction for how many Earths, based on what we know from Kepler, how many Earths this Earth 2.0 mission is going to find. We're going to find something like 20 Earths, given what Kepler knows. So if that succeeds, we'll be filling a big void in human knowledge, and I'll be very happy with my life. Okay, it's definitely not the easy way towards it. I've been dedicating a lot of hours to this, and technical problems, engineering problems comes up one after another. it's really exciting, all these problems. In the meantime, it's also a lot of headaches. So we hope to push it up to the sky at 2025, 2026, so 5 or 6 years time, and hopefully come back with 20 Earths that other missions can study them, study the atmosphere, whether it has ocean, whether it has atmosphere, or even more ambitiously, whether it has life. Okay, so that was the end of my presentation, and I'm open to any kind of questions you may have. Thank you for your patience.
Thank you, Dr. Wu. We have a number of questions in the chat.
Yeah.
So if you're okay, we'll just start with
Yeah,
first
please.
from John Govro. There are many different kinds of stars. So would being more selective in where we look help with reducing the surface noise from certain stars?
Oh yeah, that is one of our key strategies. As you said, there are many different stars. We are going to just we're going to focus on stars which are like the sun, because, okay, there are very small stars like M dwarfs, which are called M dwarf, which have about mass about half the sun. Some of the planets going around them, they are in the so-called habitable zone. So in that sense, we already know habitable planets. But unfortunately, those planets are probably tidally locked and all kind of adverse conditions for life. So we don't know if life exists there or not. So we are not going to focus on M dwarf. We want to focus on stars which are very similar to the sun in terms of mass, in terms of lifetime, and all kinds of things. So other than that, there's another very strong constraint, like you said, noise. As you can see here, some stars are really noisy, some stars are very quiet. We will be exclusively focusing on quiet stars. But to do that, that's why we have to go for lots of telescope. The reason we sort of have to use a smaller telescope rather than going for bigger is because we want to catch a bigger patch on the sky. Why? Because on the small patch that Kepler was looking at, there are not enough stars that's quiet. That's why Kepler failed. So to succeed, we have to look at bigger patch and catch those very quiet stars, and when their Earth transit in front of them.
Thank you. We have another question from Ron Bernardo. Did the Nobel Prize winner use the same methodology as Kepler in finding the first exoplanet in 2013?
No. So there's a chance for another Nobel Prize. No, they don't. I don't have a slide here. The Nobel Prize winner, you may have heard, they got the Nobel Prize for discovering extra, that's in last year, I think not this year. Last year, they discovered, for discovering the first extrasolar planet. And that was in 1995, they discovered it. That was using a technique which is called the radial velocity. So instead of looking for transit, they were looking at the wobble of the star. And not only that, the planet they discovered is a Jupiter-sized planet, Jupiter mass planet. And not only that, that Jupiter was going around the star really crazily fast. So the star wobbles a lot when the Jupiter is going around it. They're discovering a very different beast, exciting, but very different from Earth. For Earth-like planet, that technique failed. So this is really the only way to go.
I have another question from Doug Curry. I can see that in the transit method, star volatility could limit observations. How much would star volatility be a limit for radial velocity or direction detection methods?
Volatility is currently hindering the radial velocity technique completely. So because if you want to use the so-called radial velocity, you want to see the star wobble. And if you have Earth going around it, the wobble is going to be very minute. And so the star is only moving with a tiny velocity. The number is 15 centimeter per second. So that's slower than you walking. When you're walking, half a meter per second. This is 15 centimeter per second. So any kind of volatility on the surface of a star covers that slow speed completely. So at the moment, the radial velocity is throttled because of that. For
Thank you.
transit, we are also hurt by that I just showed, but somehow we hurt by that terribly, but there is still a small percentage of stars which are quiet enough for transit to be detected. So we're just a little bit better than the radial velocity. That's why I think this is the only viable technique at the moment. Direct imaging is hopeless for Earth-like planet.
A question from John Goverill. You said that you spent 5 years mining data from Kepler. How much more data needs to be examined?
Good question. So let's see. I think, so I would claim, so our work and other people's work for the past 5-10 years have mined the low-lying fruit on the Kepler tree. There may be some deeper hidden secrets, harder to get to, but those are unknown, right? You don't know. My guess is that there are, if we work hard enough. For example, let me just give an example. This transit detection. Nowadays, we use some simple algorithm to find the transit, but people have been developing more sophisticated algorithm using neural networks or machine learning to find transit. It turns out they're actually better than human eyes or better than our computer program to find transit. When that succeeds, there may be another breakthrough. So I think there's still possibly treasure hidden in the Kepler data, but they are unknown unknowns. So it's worth exploring.
We have 2 more questions.
Well, it's amazing you guys have so many questions. I love it.
From Tom Steckner. Presumably, the quiet stars are those which are more mature, but not too mature, because then they get noisy again, correct?
You guys are very knowledgeable questions. Yeah, so actually that's a very interesting question. Why are some stars quieter? Why are some stars noisier? One possibility is like what you suggested, the age. So as the sun is going older and older, its magnetic activity is going to die down a little bit. As a result, we expect the surface to become quieter. So that is one possibility, which is an interesting possibility if that's true, because that means whatever Earth we found, the Earth has been around for a very long time, like 10 billion years, for example. Maybe then it gives more chance for life to arrive. That's an interesting probability. There's another reason why stars may be quieter, which is very interesting. Turns out, even if you look at the sun over, people have looked at the sun for a few thousand years now. If you look at it over the past few hundred years, ever since Galileo invented the telescope, the sun has behaved differently. As sometimes the sun is very quiet, and sometimes the sun is very noisy. For example, there's the famous mountain minimum, where the sun is quieter, fewer sunspots, activity is reduced. So that's another possibility. We don't know. I really would love to know the answer to this question. In fact, I want the student to work on this to figure out why some stars are quieter, why some stars not. And I don't know the answer yet.
And our last question is from James White. On the sub-Earth analog diagrams, what are the 2 gray dots that approximate Earth in size and distance? What planets are these?
Yeah, you're very sharp eye. There are some dots here. Okay, some of these dots are, so each one of these dots, I didn't plot them, but each one of these dots actually has some so-called reliability score. We give them some credential to tell us whether we should trust their spots being a real planet or is it just some instrumental effect. So the problem is that there are something there which looks like they are habitable or perhaps Earth-like, but typically the ones here have very low reliability. That's just like one of the examples I showed before. We're not completely convinced they are planets yet. So yeah, unfortunately. This point, all the points here, other than these few spots, all the points here are very secure. In fact, there are lots of interesting about them. they prove themselves to be planets. But these two, at the moment, they're not confirmed, are not even close to being verified.
Very interesting. Thank you.
Well, thank you.
Oh, I have one more question that just showed up. Can you take one more?
Please.
Okay. This is from Doug Curry. What prospect is there for the restoration of the terrestrial planet finder or European Space Agency's Darwin, or a combination of that, were to fly in formation and directly detect Earth-like planets?
So as you notice, it's not here. So the terrestrial planet finder, or the mission, you guys are incredibly knowledgeable. I'm ashamed. I probably gave too simple a talk. So the missions you were mentioning, terrestrial planet finder, and I think Darwin as well, and so on, is not selected. So this mission, the missions on here are selected and funded. The reason they're not selected, there's actually sort of lots of technical reasons. Not that they're not exciting. Mostly, I think, is technology is not yet mature. They have not yet demonstrated that they will produce credible science. But another few years, in particular, after we find those good candidates of Earth, I think it will revive those proposals, because it shows to European Space Agency and NASA, and hopefully all the other space agencies around the world, that there are something there worth looking with bigger and more powerful, more advanced telescopes. So at the moment, probably next 10 years is going to be hard, but 10 years later, who knows?
Dr. Wu, we have two final questions, and these will be our two final questions for this evening. So the first one is from Bernie Benass, and he asks, how can citizen science help?
I'm sure you guys have helped. No, are you involved with some of those visual inspections of planet transit light curves and so on, or?
No, we have not been, although that's an area that amateurs can get involved in. And I know Bernie and I were talking about this before, both that aspect and also, and this isn't pertinent now, but after, we're going to point out that there are actually stars out there that where planetary transits are within the range of amateur scopes. And perhaps we can encourage people to go out and observe some of those. So, but no, we haven't been involved in that aspect, but that's a possibility for people out there.
Okay, let me first make it bad news and then the good news. Okay, the bad news is that for larger planets like Jupiter type of planets, you can see it from the ground, and possibly even with amateur sized. Some of them have bigger telescope than I do. Amateur-sized telescope, bigger planets. Earth-like planet is impossible to see it from the ground with any telescope, even the biggest one in the world, because the Earth's atmosphere is just too turbulent. That's the bad news. Okay, what's the good news? Amateur telescope has an interesting niche, that is discovering Earth-like planet, not using transit, but using the so-called micro lensing, which is using Einstein's general relativity, where the planet acts as a little optical lens and deflect the starlights from behind and focus it towards us. So stars suddenly gets brighter. So that's called micro lensing by planets. And now it's becoming known that the universe have Earth, we're one of them, but those Earths may come into two forms. One form is Earth going around stars, so likely to have life. Another form is called a free-floating Earth. For some reason, the universe have quite a lot of those planets which don't belong to any stars anymore, but just floating into interstellar space. And from time to time, they focus the starlight from behind them, and then we know they're there. This is called microlensing. We are actually currently discussing putting a little microlensing telescope on our mission, Earth 2.0. And where does the amateur astronomy help in that case? Okay, so Earth 2.0 is going to be staring at a field, and if it sees a microlensing, it's not a very big telescope, but if it sees a microlensing event, if amateurs also see the same event from the ground, which is way possible because microlensing is a very substantial event. It has been proven that there's a lot of amateur which have caught it. If amateur astronomers on the ground also found it, caught it, comparing the two microlensing curve, we can determine the mass of those free-floating Earth. So that's where the interesting come in, right? Let's imagine we caught it on our mission, and then we send the alert around the world to amateur astronomers and say, look for that patch of the sky, that particular patch, and look for the light changing of that patch, and record the light change and measure the microlensing event on the ground. Because our mission, the space mission and the ground are separated by some distance. So we can do parallax to the event and we can measure the mass. So that's actually a really powerful way of this finding another kind of Earth. So that's one idea we are now talking about. But there are lots of other events. I think amateur astronomers are required almost at some degree.
Okay.
Thank you. Fantastic. I didn't mean to. My apologies. I didn't mean to imply that Earth-size transits could be were visible from the ground, but you explained that perfectly. That's great. I'm gonna pull a little rank here and just ask another question, if I may, to go back to the Earth 2.0 mission. Which sounds incredibly exciting. Can I just ask a couple more questions about that? Do you know what the planned duration of the mission is? What the sample size you're hoping to get? How many targets you're hoping to get out of it? And you showed us that Kepler's spent its time looking in the Cygnus region. Do you know where you're going to be looking with the 2.0 mission?
Right, this is a great graph for that. Okay, so first is that we're going to run at least 4 years. And as any kind of space mission like this, what you do is that you, in principle, you can extend it because you get energy for free from the sun. You have solar panel. The only expendable is a little bit of fuel to fine tune the telescope. So we want to run for sure 4 years, probably 6 years, because we will have enough fuel to run. And if we're lucky, we can get to 8 years if our reaction views don't fail like Kepler does. Okay, so 4 years minimum. So this projection is based on 4 years projection. How many Earths we're going to find? We'll be staring at close to, actually, number of stars, total stars we're going to be staring at is not that different from Kepler, but we are going to choose only quiet stars. So we're going to stare at 200,000 stars, for example, and we choose them to be very quiet. You saying which direction on the sky we're staring at. So this is the Milky Way, Cygnus region. The Kepler field is a little bit, I don't know if you can see it, it's in there. So we are still discussing different strategies. Why do we have different strategy? We're going to stare at the same direction, but we have 7 telescopes, so we have some freedom. We can either pack all 6 into the same circle, or we can split it like this, or split it like that. So we've been doing a sort of yield estimate based on how we pack the telescope on the sky. The moment this one wins, the green one, which is the lowest most one, it turned out packing all 7 telescopes in the same direction is the best. But we're still doing calculation to make sure that is the best strategy. But in any case, we'll be close to the Cygnus region. Does that answer your question?
It answers it perfectly. Thank you very much.
Thank you for your enthusiasm.
Sue, are we good there on your end?
I have 2 more questions, John, and we can handle it one of 2 ways. We can go into break, and I can do the questions through the break for people who want to hang around and listen, or I can just do them now. I'll let that be your call.
So, well, sure. If there's two, Yanqin, are you okay with two more questions?
No, the more question, the happier I am.
Okay, fantastic. Well, Sue, fire away then. Yes.
Okay, this is from John. You got to turn off your video though. This is from Tom Steckner, presumably, and I hope I don't mess up the pronunciation of stuff in this question, so I'll do my best. Presumably, at least half the stars aren't worth looking at because they are double or multiple, correct? So between age, metallicity, and multiplicity, we need a large-scale spectroscopic survey similar in size to Hippocos or Gaia in order to weed our candidates. Is there anything like that coming?
Wow, all these expert questions. That's exactly the kind of question we spend our daytime calculating. Okay, so yes, we want to weed out noisy stars. We want to weed out binary stars, triple stars, and we want to weed out any kind of giant stars. Metallicity, I'm not so sure what we should do. I don't think we want to weed out one way or the other. But we are definitely weed out all these other things that some of them mentioned in you. We want to weed out enough stars that are potentially, they're hopeless anyway. On the other hand, it's a dangerous game to do it like that. It's we are going to get, in astronomy, this is called biased view. You're going to get a view of the universe, which is not quite complete. So yeah, I don't know if that answers your question. Maybe you want to ask it a bit more detailed. But yeah, we are taking a lot of precaution. And currently there are large astronomical surveys which provided us exactly all those information, binarities, activities, age, metallicity, everything. For example, the European Space Agency had the Gaia telescope. That one is really worth its money. It's a treasure trove for us. So we're using a lot of information from those and ground space surveys.
Tom said that answers his question. So
Thank you.
You answered this question well. All right, last question is from Ron Bernardo. I noticed the lens setup and orientation of your project telescope are pointing at different directions. Is that to offset the failure made by Kepler?
Oh, wow. Interesting. Let me explain a little bit, but that's an interesting question. At the moment, as I said, we're still not completely sure what to do with the seven little dwarf telescopes. In this picture, it's depicted that they are shining at different directions. But most likely, in the end, we're going to converge them on the same direction and just stare, like this picture shows. Every yellow square, every yellow circle, overlapping right on top of each other. It has the advantage that we can probe the deepest in this point, but it has the disadvantage that we're missing all the other fields where there could be very quiet stars. They're also very bright. So we're still agonizing over it. Is that your question? Or are you asking something else? This is just the artist's conception. Yeah, this is not how it's actually going to be assembled.
I think that answers the question.
Thanks.
So thank you. I'm going to turn it back over to John.
Wow, that was rapid firing of questions. Thank you all. That makes me feel happy. I feel accomplished.
So, well, thank you, Yanqin. That was absolutely fantastic. And I hope you realize how enthusiastic everyone was and how keen they were with the number of questions that were flooding in. You've obviously captured their attention, their imagination, and I'm sure everybody that's tuned in tonight has found it as worthwhile as I have. Thank you very, very much.
Thank you. I found it very worthwhile for me to hear all these intelligent, enthusiastic questions. Makes me happy.
Oh, well, that's good. Thank you. I'm glad you did find it worthwhile. So our heartfelt thanks and appreciation for your time tonight. Just wonderful.
And I'm probably not going to stay on after this. I heard that you're going to have some social gatherings. And let me just express again how admiring I am of all your interest in science. It's very remarkable. And I hope you have a good weekend. And see
Thank you
soon.
so much. And you too. Thank you.
Thank you. Thank you all.
So everybody, that was absolutely wonderful. I can't say enough good things about that presentation. It's what we'll do now is we will take a brief intermission. Of course, when we come back, we still have Matthew Mannering with the Sky this month and some door prizes, very special door prizes to hand out. So we'll take a brief intermission now. It's 8:38, 8:39. How about 8:45 we come back? All right. So, and we'll see all of you then. So.
Okay, I'm gonna leave and good night.
So,
Thank you.
thank you so much. Good night.
Bye.
Thank you.
Good night, and thank you.
John, how many door prizes do we have tonight?
We have 4.
Thank you.
So, and Sue, you'll be on the lookout. Swapna's had another engagement and she's joining us late. And I told her that we would hold off on the door prizes until she is able to join us. And so if when that happens, if she might be here by the time we get back from break, and if not, then we'll carry on with Matthew, who's expecting to come after break anyways. And then we can save the door prizes for the end. But you can let me know if Swapna's joined us by that point.
Not here yet, but I will definitely let you know.
So perfect. Thanks, Sue.
All righty.
See a word for John.
So hi, Ed.
That book that you were holding for me, it doesn't look like I'm going to get over there any time soon. So why don't you just add that to the 4 that you're passing out tonight, and somebody else
Okay.
can enjoy it.
Okay, well, that's wonderful. Thank you, Ed. I very much appreciate that. I'll tell you what, we have the package for tonight already. So if it's okay, if I don't cross paths with you by next month, I'll include it in with next month's prizes, if that's okay, since I'm already all set to go tonight. Is that okay, Ed?
That works for me. Thanks, John.
Excellent. Thank you, Ed. Appreciate it.
Well, I think that was a really, really excellent talk. I'd like to, I know our speaker is left for the evening, but I, for one, was extremely impressed with that talk. Hey, Matt.
Everyone can turn on their video and their audio and chat during the break. Please feel free to.
Well, there's Kevin. What's that growing on your face, Kevin?
I know. How's it going, Jim?
Good to see you.
Coronavirus, I know. Nice to see you. Long time no speak.
Yeah, you bet.
That's there, Kevin.
How's it going, folks?
I saw an interesting sight this afternoon while I was coming back from Paris. There was a chap pulled out of a laneway, and he had a pier mount set on top of his car, and it looked like he had a solar telescope attached to the top end of it.
Excuse me for a second.
I had my solar telescope out a couple of days ago, and turns out I missed seeing a flare by about 2 hours. So it was about 2 hours too late. Of course, you never know when they're going to happen, but the area that I was looking at flared quite nicely just 2 hours before. That was kind of a bummer, but it was still interesting.
Yeah, I'd like to congratulate whoever it is that got that speaker. She was great.
Well, that you want to be thanking John on that one.
The other thing also that was great is that it was better diversity than we sometimes have.
Absolutely. She was wonderful.
Yeah, but I mean also from a diversity perspective in terms of who we have in our speakers. That was great.
Yeah, I agree with you 200%. Yeah. Somebody's typing.
Yes.
Dan, are you getting set to do your Santa Claus setup there? Or you're looking really Santa-ish.
I'm not really a Santa Claus.
Don't mind me, Dan.
Somebody's typing like crazy.
There you go.
Good.
There's the hat
I do have a hat.
on. Oh, Chris, you're
And
looking
Dennis got one.
Santa-ish as well.
Denise from Chris.
Yeah, Dan and I must shop at the same store.
There you go.
I've only got half. I've only got half. I haven't got this part down here. I've only got the little part.
There you go.
That's it.
And see, and of course, the family Whitman is sporting some very elfish look.
Yes.
Yes.
Nice ears.
I want to know.
Excuse me.
What's going on with typing here?
Mm-hmm.
We're all oddly quiet tonight, all night.
Oh, Chris, are you asking what time the pickup's going to be for the calendars tomorrow? The porch pickup? I don't know.
No, just there's a line going through the M, so it looks like 2 days.
That was me teasing earlier, Jim, about when she
Oh, okay.
what
Okay.
time the porch pickup to get the dessert. Whitman's had the.
You know, if anybody's asking about the calendar pickups tomorrow, it's between 1 and 3.
Yeah, we got
in the
ours.
lobby of our building.
No, we got ours. Thanks. No, I want a porch pick up the dessert she's making.
Chris, this is for Chris Stretch, if he can hear me. Sue is having some computer issues at the moment, so if you could look after making sure the meeting runs properly, that would be great.
Okay, I will.
Back in soon. Thanks.
So Jim, how many extra calendars got ordered?
I'm not 100% sure. John's got the listing of what was ordered.
50. We ordered an extra 50.
50. There you go.
Well, yes. Yeah.
Dan, I thought Santa drank Coca-Cola, not Pepsi.
Yeah, but it's what else is in the Coca-Cola.
Testing 1, 2, 3.
Actually, I mixed Coca-Cola and Pepsi and put it all in a Pepsi bottle.
But where's Grant Dixon? Where's he hiding? I'm afraid to move any of these pictures for fears of losing the hue.
Michael, is that you speaking?
No,
Why
not a
don't you turn your
chance.
camera on so we can see your
How do I
face?
do that?
Well,
thought
you down
Sue
the
did that.
bottom right-hand corner of your screen, you'll
There
probably
should be
see
a
a thing that
stop
says
video
stop
icon.
video, on video. You click
Hang on.
there.
Left.
Stop video icon at the lower left.
Yes,
Yeah, lower
What
left
one?
corner of your screen.
yes.
That one?
I get blocked by host.
Talk to Cortina? No. Which one is it? Doesn't look like that one.
Michael, you know what? That's okay. Don't worry about it right now because we're going to get going again. So I'm just going to, if you get it on, I'm only going to make you turn it off again. So,
Okay. Well,
so,
thanks.
so that's okay.
You know,
So
Grant was
we-
mentioned. Sorry.
No, go right ahead.
I was going to say that Grant was mentioning a radio telescope at the beginning of the meeting.
It was, yes.
That sudden ionospheric disturbance detector that I built years ago and ran with Stanford University, we could get that thing fired up again. It could be a great club project.
Don't see why not.
Economic victory.
They're not expensive.
We just have a lot of old guys out here that have interesting careers, and some of them spill back into what they do in their hobbies. He happens to have a radio telescope because that's what he did. And he also has a vineyard which he likes to make wine. So a man of many talents. So if you're not listening to the stars, you're drinking wine at his house. Very
Yes,
interesting.
yes. and maybe see more stars than ever.
I'm sorry, I'm back and forth as I'm forced to be the cook while we're doing this, so I'm using my time wisely.
And I know Grant is an excellent cook. So,
but I'm listening.
So
He makes good coffee too.
If we're ready to begin, we'll resume with the second half. So once again, I'll ask all of you to mute your microphones and turn off your cameras, with the exception of Melissa and Swapna. If you wouldn't mind staying with us for a moment, I need both of you, of course. So Melissa, who have you got with you on your end doing the
the master.
So there we go. Fantastic. Good to see you. So let me just, you're just a tiny little picture there. So wonderful. That's great. And do you have the list for tonight? You've got all the names?
We do.
Yes, we do.
So yeah, Sue got the names over to you. Fantastic. Okay. So in that case, before we move on to Matthew with the second half, we have door prizes to hand out. It's always been our custom every year for many, many years now. We've included a social event in our December meeting, an extra long break to spend with fellow members and friends. Many of you often bring treats and goodies to share. And it's wonderful. You remember last year, it was our first and so far only holiday social at the McMaster Innovation Park, and it was absolutely wonderful. I couldn't have asked for better. Well, of course, we can't do that this year, but it will just make next year's social all the better when we get to come back and see each other again face to face. For now, though, we do have some very special door prizes to hand out this month. A big thank you goes out to Swapna Shrivastava. Swapna, did I even come close to pronouncing your last name correctly?
That was perfect. Thank you.
Okay, good. Excellent. And so a big thank you to Swapna and her family for donating 4 Amazon gift cards worth $25 each. All right. So we're not delving into our usual bag of books. Tonight, you get these special Amazon gift cards. And a big thank you to Swapna for her very generous donation. So if you are a lucky winner tonight, the great thing is you also don't have to leave your house and come here to pick it up. We'll connect you both, and we'll have it emailed directly to you. So I will now very gladly hand it over to Maya. So hi Maya, how you doing?
Good, how are you?
Wonderful, smashing hat, I must say. Wait a second, I have to get my Christmas hat on here since we're doing Christmas hats. Here we go. Okay, there's my Christmas hat as well. So I'm going Dickensian for this. So, all right, Maya, I can't wait to see how this works out. Fire away. It's all yours.
So the first name that we have picked using our traditional percentile dice was Pam.
Pam who?
Just Pam.
Someone who's on the list just as Pam. Pam, are you with us?
Yeah.
Hi, Pam.
Hello.
So Pam, if
Yay.
afterwards, if you're able to email me directly, okay? Email me, chair@amateurastronomy.org. All right. Just email me directly at chair, and we will get you connected with your prize.
Thank you.
So congratulations. Who's next, Maya?
John Govro.
Okay, that's me.
That is you. That is you.
Fix.
And it's the nice thing about this is that we know it truly is random the way we're doing it. But just toss my name out and give it to somebody else. So
In anticipation that you said that, we did draw a couple of extra names.
oh, okay, there you go. So,
But we thought we'd throw it out there just in case you would accept. So the next person is
our 2B is Bernie.
Well, I'm not going to be giving it back.
Bernie, congratulations, Bernie.
Thank you very
know
much.
What to do. Bernie, you know what to do. Just email Swapna directly, okay?
Okay.
All right. Good. And who's number 3, Maya?
Number 3 is Philip. How do you say that?
Guys?
I don't know how to say his last name. But Philip. Philip G.
What?
Philip
Philip, what's
G.
his, with a G?
Yeah.
Good.
Philip,
Philip, are you with us tonight? Are you still with us?
John, Philip was here at the beginning, but he appears to have left the meeting.
Oh, he's departed the meeting. Okay, that's unfortunate.
We have extra
Okay.
names if we want to just move on to whoever's here.
I'm afraid we'll have to. Yep.
In that case, our next name is Al Murphy.
Fantastic. Al, are you with us tonight?
There he is.
I am.
Excellent.
Yep.
Congratulations, Al. Same
Okay.
instructions. Just email me directly, okay? chair@amateurastronomy.org, right?
Got it.
Just email me at chair and we will hook you up.
Thank you.
So there's 3 of them, Maya. Who's number 4?
Who's number 4? Well, number 4 is Jeff.
Jeff.
Just Jeff.
Jeff.
Just Jeff.
Come in, Jeff, over.
Because that's how you're logged on. So that's how you're logged on. So just Jeff, are you here?
I think that could be me, John.
So okay.
Really certain there's only
Yep,
one Jeff.
Just
How about the odds?
So okay. So Jeff, same instructions. Just email me, okay?
Okay.
So and we'll hook you up. So wonderful. So Pam, Bernie, Al, and Jeff, congratulations. Well done. Enjoy it and spend it wisely. So congratulations to all of you. And again, a big thank you to Swapna and family for their generous donation. So I'm sure they're very happy people out there. Yay. So, And with that, thanks, Maya. Stellar job as always. That's wonderful. So with that, what I'll do is I will ask those that have their cameras on to turn their cameras off so that we can throw our attention over to Matthew Mannering, our observing director extraordinaire, who takes the time to put together a splendid article in the Event Horizon newsletter and a wonderful presentation to deliver us here live each month. Matt, I hand the floor over to you.
All right, let's see if we can make it work. Screen share. Screen sharing.
Lovely.
Okay, can everybody see the slide?
Yes.
Coming through perfectly.
Wow.
All right, and off we go.
Yeah, an Arecibo.
So welcome to the sky this month for December. I'm going to start this talk with Arecibo, as many of you know. It took some damage about 3 or 4 months ago. Some of the supporting cables holding the dish snapped from rot and age, and it created this great big crater in the dish. They brought in 3 or 4 different teams to, somebody still got their microphone on, by the way. They brought in 3 or 4 teams of engineers, and they looked at it and they determined that it would be too dangerous to fix. So they sent the teams away to figure out how to dismantle Arecibo. In the meantime, this great big package up here, instrument package, about 900 tons, decided to leave the stanchions it's on. So here's the view under the dish. After the first damage, you can see that lots of it has fallen in, and if they had gone in to try and repair it, there was a very real risk that the whole thing would collapse on workers and kill a bunch of people, and that's why they determined it had to be scrapped. And then the whole instrument package came down and broke off the tops of the pylons, and it's actually on video. If you want to look it up, you can actually see the moment that everything snaps and the thing falls to the ground. So that's that for Arecibo, and it's too bad. It was in service since 1963 and has done lots and lots of amazing work, both deep space and in terms of things like near-Earth objects, tracking them, figuring out their orbits, size, shape, all kinds of things, and many other things. So if you want to see how this all happened, you can just sort of Google it and find out lots of cool stuff. An unfortunate end to it. Also, SpaceX just sent one of their Dragon cargo carrying ships up to the ISS, and it was their special 2020 Christmas delivery. And so that, I'm sure the crew up there was really looking forward to it. And they actually increased the size of the cargo hold. So now it's as big as the crew capsule would be, which gives them about, I think, about 20% more cargo space. And it's the first time that a cargo vessel has actually docked automatically with the space station. Up to this point, the robotic arm was used, so that the ship would come in close and sort of come to a stop relative to the ISS, and the robot arm would pull it into position at the airlock. So that's another big change. So what did Santa bring to everybody on the ISS? Very important question, I would think, if you're up there, and one day is pretty much like the other. So all the presents, of course, those are secrets, but we do know about Christmas dinner. So they took up roast turkey, cornbread dressing, cranberry sauce, shortbread biscuits, and tubes of icing, amongst other things like fresh apples and oranges, which I'm sure were very much appreciated. Out of the 6,400-pound load, they also included billions of microbes, crushed asteroid samples, and 40 mice to do experiments with. Now let's hope they didn't get this mixed up with that, because that would be unfortunate for Christmas dinner. What about the fruit cake? I mean, really, isn't that Christmas to get fruit cake, whether you hate it or love it? It should have been some fruit cake. Well, it turns out 2 years ago they did send fruit cake, not shortbread. And just a couple other stupid facts about fruitcake. December 27th in the US is National Fruitcake Day. And that's all I'm allowed to say. But I've come up with another day, the next one, which is December 28th, which is how to re-gift your fruitcake to somebody else. And then in the States, there's also January 3rd, which is an actual day where they have Fruitcake Toss Day. And they break it down into different categories, 2 pound, 1 pound fruitcakes, and you can see how far you can throw the suckers. So we'll see what happens. It turns out that 40% of all fruitcakes are re-gifted at least once. So you can tell that it's not exactly the most popular, but that one looks pretty good. So I said it had gone up into space before, and it turns out that they sent fruitcake to the moon with Apollo 11. Now, it doesn't look like a bad size sort of piece on your monitor there, but each of those 4 little pieces was a 1/2 inch square. So that's not a lot of fruitcake. But interestingly, it didn't get eaten. It came back and it was re-gifted to the Smithsonian. And there it lies, some whatever, so now 50 years later, still uneaten as far as we know. Why would you send shortbread? Well, I got my wife's most excellent shortbread out of the freezer, calculated the volume, weighed it, got the density, and it turns out that her shortbread is 0.67 grams per centimeter cubed, whereas fruitcake comes in at roughly 1 gram to 1.2 grams per centimeter cubed. Why is that important? Because every single pound you send up into space costs tens of thousands of dollars, if not more. So not only is it more efficient in terms of getting it into orbit, but it's also much more preferred by more people. Moving on, I just read this like yesterday or the day before. There's a new telescope being commissioned. It's called the Daniel K. Inouye Solar Telescope. It's really a phenomenal achievement what they've done here. And as you can see, the location is stunning for this new telescope. Well, it's on Haleakala, Maui in Hawaii, and it's going to come on to full service in 2021. Nice big 4-meter mirror. They've increased the resolution on the surface of the sun from roughly 75 kilometers per pixel down to 30. And they actually use just over 11 kilometers of cooling tubes in the telescope and the observatory to keep it at an even temperature. The solar images I'm going to show you are from first light, which was way back on January 29th. I don't know why it took this long for the images to be made public, but they were just recently released. So there's an image of the telescope in the observatory. Lots and lots of tubing, as you can see already, before it does anything else. And here's a full solar face image with the inset showing the field of view of the new telescope. And if you look in the inset, you can see each of these little yellow nodules are actually cells of plasma coming to the surface through convection. And you can see one cell is roughly the size of Texas. And there's a tiny, tiny, tiny little white dot there, which is roughly the size of Manhattan Island. And those and all these other little very bright parts are magnetic fields that show up on the sun. And they're thinking, that this is why the solar corona is so hot, is that these magnetic fields play some function in releasing the energy up from the surface. So here is the actual image, roughly 36,500 kilometers square. And it kind of looks like creamed corn to me a bit, but those are all cells of plasma. And there's a movie on the Inouye website that covers a couple of hours, and in it you can actually see the convection occurring over this area. It's pretty fascinating. They also took a picture of one of the very few sunspots around in that whole period. And as you can see on the right, the umbra and penumbra are just beautifully detailed. And of course, those wavy lines are all due to magnetic fields, and the structure is just amazing. And what I would think would be really interesting is see a movie of that over hours and see how the actual sunspot evolves. I'm looking forward to that at some point. Here it is, full size, and it kind of reminds me of Van Gogh's sunflowers. We've seen that in the gallery in London years ago, but that's what it reminds me of. It's beautiful. Moving on, The Geminids are coming in just a few days. Now, early on the morning of December 14th, there's a very narrow peak of only about 2 hours where the rate goes from 30 or 40, all of a sudden up to around 150 an hour, and then just drops off like off a cliff a few hours later. But you can start observing it before midnight, and when you start is up to you, but I would wait until Gemini's up in the sky and then just keep watching there and watch for, these are bright ones. There's quite a few of them and they're really quite bright. So with a new moon, it should have quite a good show. The other big event of December is the conjunction of Saturn and Jupiter. And you can see Bernie sent me this graphic, and it goes from early October right through December 21st, which is the conjunction. And you can see how the two planets visually appear to come together. Now on the 21st, there'll only be 6 arc minute apart. And 6 arc minutes is extremely close. And in fact, some people will see them as a single point of light. Others will be able to detect that there's a minor gap between them, but it's going to be extremely close. And in fact, a conjunction like this hasn't happened in 400 years. And I think if I remember correctly, the last time it was visible from this latitude was 800 years ago. So this is an extremely rare event. Don't wait for the day. Start observing now. If we ever get clear skies, that is. Start observing now and watch it. And then once the two planets are within a degree, you should be able to get them in a low power eyepiece on your telescope in one field of view. And as they get down to about half a degree separation, you should be able to see the planets and their moons all together in the field of view. This is a case where you don't want extremely high magnification because you want to make sure you get everything in the field of view. You don't want to cut anything off and have to bob around with the telescope. So somewhere around medium magnification, giving you about a half a degree true field would be correct. And here, if you can imagine kind of a circle going around this area here, that would be the view in your eyepiece. And at that particular time, that's around 5:45 on the 21st. You have a window from about 5:15 to 6:30 to view this, and then they get too low to the horizon. They'll be below 5 degrees. It'll be extremely difficult to see them at that point. Oh, now it's telling me I have to go to Stellarium. So off I go. So, going to bring up Stellarium. How will this go away? Is it coming up? Here we go. Okay, so the first thing with Stellarium, this is free, runs great on a PC, is I'm going to set the time and the date. So I'm going to go to the 21st, like this, and then I'm going to back off to 5:30 in the evening. Unfortunately, it won't let me save the settings and the time and date at the same time, which is a real pain. So coming around, first thing is ignore the moon. There's a quirk in Stellarium where if you make the really bright stars brighter, it for some reason thinks moons are stars and it blows them up as well. So just ignore the moon. It's obviously nothing like that. So here you can see in the southwest, you can see right there that Jupiter and Saturn are close together in the sky. And in Stellarium, if you click on an item and then hit the space bar, it'll center it. And then you can just use your mouse to zoom in. And there you go. There's the view right at that time. And of course, you can play with the times and the dates and everything and see how things move around. It's really a very useful program. So I would say for the first hour, so till about 6:30, that's what you want to be looking at, especially that evening. But I thought what would be interesting is that it's also, of course, the longest nighttime day in the year, the most dark hours. And from where we are at this latitude, of the 20 brightest stars, we can see 14 altogether. And it turns out you can see all 14 on that night and of course on the nights surrounding it. So what I'm going to do is I'm going to move forward here till 6:30, so it's dark. And then I'm going to just zoom out a bit, pull it down. And where Saturn and Jupiter disappear into the ground, that's roughly where you're going to start, in the west to the southwest. And low above the ground here, there's Altair. That's the first of the 14 of stars that we're going to just sort of key on. And another star that's got nothing to do with the 14 is this one here, Terra Z. Terra Z, for some reason, if you have a go-to scope and you're doing your alignment, quite often, instead of picking Altair, it will pick Terra Z for some reason as one of the alignment stars. So that's a really useful one to know where it is. Of course, up to the right is Vega in Lyra. And then up above that is Cygnus. And at the tail end of Cygnus is Deneb. Now, this is all the kind of stuff you want to do with just a nice pair of binoculars, 7x50s, 8x42s, 10x50s, whatever your pleasure is, and just bomb around the sky using your binoculars. And especially if you're still learning constellations, keying off of these very, very bright stars gives you an idea of where you should be looking. So after you've had a good look at those, you're going to turn to your left, which is to the east. And now you're going to be facing south. Now, you see that little star there, Fomalhaut? It's really, another name for it is like the loneliest bright star in the sky, because if you look around here, there's not another first magnitude star in this whole field of view. So if you start facing south at about 6:30, just low above the horizon, maybe 15 degrees, you're going to see Fomalhaut. And it's a beautiful star. And it's really impossible to miss because there's nothing around it that looks anywhere near as bright. So after you've had a good look around there, you're going to see that the moon, which is totally wiped out by stellarium in this case, is actually almost a perfect first quarter. And then if you've got your telescope out, it's a great time, of course, to look at the Terminator at first quarter. And then Mars is up here. It's getting small fast and getting dimmer every day. It was a great approach this time, and a lot of us saw some nice details. So hopefully you got out and had a look at it. Now, after you've done that, you can actually go in, have some hot chocolate, and wait till about 9:30. All right, that'd be about the earliest you want to go out and turn to the east. And if you do that, you're going to find Sirius in Canis Minor, very low to the horizon, but up high enough to see. You're going to see Procyon. Did I say Canis Minor? Canis Major, I'm sorry. And over here, Procyon and Canis Minor. Now, the little dog is really a little dog. It's 2 stars in that little line. I think it's a little wiener dog. Doesn't look like anything much other than that. And the other thing of interest is Procyon and Sirius both have white dwarf binaries or second stars that orbit the main star. Now, white dwarfs are stars that have basically gone through their life cycle, gotten huge, gone through the crunch, and now they're just really small, sort of smoldering wrecks of stars. Thing is that when they compress, all that energy of compression has to be released. And so they shine very, very brightly for many billions of years before the energy is finally released from the star. So after you've had a look at those, of course, Orion's your next stop. And you've got the Great Nebula there. Rigel is a beautiful blue-white. Betelgeuse is that orangey red. And if you want something a little bit different to look for the belt. And then with your binoculars, look for what I call the snake. There's a line of stars that goes right through here. And the first time I ever saw it was with binoculars, and I didn't realize that it even existed. But ever since that day, I've called it the snake. So then you can move across to Gemini, and here the twins are laying on their side. Here's their 2 heads, and Pollux is one of the 14 stars that you would want to make note of. And then going up, you hit Auriga, and you hit Taurus over here. So if you go to Taurus first and Aldebaran, it's a reddish orange star. It's really bright. It's beautiful. You can look at the Hyades here, a beautiful cluster of stars, especially in binoculars. And while you're at it, just go straight up. You'll hit the Pleiades, again in binoculars, spectacular. and then head over to the east, which is your left, to hit Capella in Auriga. Capella is super bright. You cannot miss that star. And while you're looking at that star with your binoculars, I'm going to zoom in a bit. Have a look for the kids. That's these 3 stars in this triangle here. And it's not like children, like, little kids. These are actually little baby goats, because for some reason, the charioteer, Auriga, is carrying baby goats in his chariot. I don't know why, but that's what it is. It is what it is. So now you're done until the next morning. So you may as well have a good sleep, set the alarm, and then come back at, I don't know. It looks like 5 a.m. would be good. And you're still looking east. Now, when you do that, you're going to notice over here that Vega, one of the first very bright stars you looked at the night before, is back up in the sky. So we've gone, more than 180 degrees around. And up here, you're going to have Spica in Virgo and Arcturus here in Bootes. And both of these are fantastic. If you have a decent sized telescope and really, really good seeing conditions, you can go to this one right here, Eta Bootes, and you can see if you can split the double. It's a tough one. It shouldn't be, but it is. It's tough. And that second star, which is really very small and dim, is like a purpley blue color. It's just gorgeous when you see it. So now you've got 13 of your 14 stars. So now you have to wait until about, I'm moving forward in time to about just after 7 a.m., just before the sun gets up and the glow is still manageable. And if you're looking to the southeast, you're going to see nice bright Venus about 10 degrees above the horizon. And if you split the difference between there and the ground, about 1 binocular field down and slightly to the right, Antares is going to be in the glow, and it's another red star that you should be able to pick out still. It's bright enough that if you look at the right time, you'll be able to pick it up as long as you got a nice clear horizon to the southeast. And if you can do that, you'll have seen all the 14 of the 20 brightest stars in the sky from our latitude that you can see at any time of the year, but now you can see them all in one night. And it's going to work. Hang on, there you go. It worked on the second to the button. So I want to wish everybody Merry Christmas and Happy Holidays, all that kind of stuff, and a very happy, safe, and well New Year. So everybody, I hope in the summer we can all get together by then and do some public nights and some larger group observing together. It's been a long time since we've been all able to get together, and I think everybody is looking forward to spending some time together and having a drink of coffee and looking through the telescopes. So I wish everybody the best and good luck, and hopefully see you sometime this coming year. And that's it for me.
Thank you, Matthew. Wonderful as always. Very much appreciated. So that was a wonderful tour, and I'm not sure I have the stamina to stay up all night to complete that tour. So if you can, you're a better man than I. So thanks, Matthew. That was excellent. Any questions for Matt?
I've got no questions here.
All right, splendid. Thanks, Matthew. I have just a couple of announcements. One is
can I say one thing?
Of course.
Sorry, I forgot to mention Janice. This month, when I wrote the sky this month for the EH, I had one heck of a time even getting my thoughts to go down on paper in any kind of coherent manner. And she sat down and sort of rewrote about half of it so that it made sense. So that was kind of, I really appreciated it. Normally she does spell check me and make sure I haven't got my words in backwards, but this time she went the extra mile and really made a difference. So I just want to say thanks.
So, yay, Janice. Thank you, Janice. Good job. So I have just a couple of announcements. A reminder that next week will be the December council meeting. All members are welcome to join in. Council meetings are done through Zoom, just like this. If any council members, I will expect to see you there, and I look forward to that. Any other members, if you would like to join in, you are more than welcome. Just get in touch with me directly, and I will make arrangements for you to join in. Also this weekend, you'll see an email coming out announcing that the beginners group is going to be revived in 2021. We expect to begin the beginners group in January. For those of you that have been through it before, you know that it's a series of seminars aimed at an absolute beginner, and it covers anything from, you know, which end of a telescope to look through and what am I supposed to point it at once I've figured that first part out, where do I point it in the sky, and all kinds of things. It's a terrific opportunity to encounter other beginners within the club and connect with some of the more experienced people to get so that you can get going. It's a lot of fun. It will be done via Zoom. It's open to everybody. And if that sounds like it appeals to you, keep an eye out for the email coming out this weekend. Are there any other announcements that I'm missing? I have a final comment, a final remark. Is there anything else I'm missing? Anything anybody needs to say before we sign off?
Yes.
Yes.
That tonight, I'm going to keep the meeting open for about a half an hour or so afterwards. Unless, am I stealing your thunder, John?
No, not at all. That's perfect.
We're going to, I'm going to keep the meeting open since we can't have our Christmas social. If people want to continue to chat a little bit, you're welcome to hang out, and if you need to go, that's perfectly fine too.
Wonderful. Excellent. That'll be very nice. Thank you, Sue. Very much appreciated. So thank you to everybody who's worked behind the scenes. Sue, Chris, Maya, and Melissa, Swapna, Matthew, everybody who came together to make tonight's meeting work. Congratulations to our door prize winners. Don't forget to get in touch with me so that we can connect you with your door prizes. I have just a quick parting comment before we go. I actually have two comments, actually. For those of you, and I don't know, there's about 50 people in these meetings, and I expect maybe 2 or 3 of you might actually read my chair report in the newsletter each month. For those 2 or 3 of you that actually do read the chair report, the little arrival we were awaiting when I wrote that arrived today.
Oh, hooray!
So arrived today. Yep. So there's a new member of the family.
Congratulations.
Thank you.
Congratulations.
So
Yes,
thank you very much.
Congratulations.
So we're once again grandparents. So a new little one came today. So you know what? So just in closing, I want to say that, you know what? I mean, we all know that this has been a remarkably challenging year for all of us. I've been very fortunate. I've not lost anyone close to me to the pandemic, but really, you know, I mean, look at us doing this, right? You know, all of our lives have changed because of us. And the club has changed too. We began this year in our new home, McMaster Innovation Park. We had exactly 4 meetings there in our wonderful new high-tech room before the pandemic shut us down. We had a period of adjustment, not knowing how to move forward, even what each passing month would hold for us. We saw schools close, libraries shutter. With them, we saw our outreach programs close as well. We do 40-something outreach events per year in schools, churches, libraries, parks, things like that. This year, almost all gone. Our telescope loaner program and our lending library shut down, and Binbrook even closed for a while, and we became housebound, unable even to take our telescopes out to the park. But we have adapted. We've entered a new phase. We have meetings online. They get better and better as we go along. We've had some wonderful speakers like Dr. Wu today. I thought she was fantastic.
Mm-hmm.
We have found ways to share our content through social media and other venues. We have put out a great calendar this year Our website has more and better content than ever. The beginners group, as I said, is about to be revived, and it turns out that observing can still be fun, even though you're socially distanced. Recently, I've even had the opportunity to actually see some of you face to face. Well, sort of face to face, behind masks, so only sort of face to face. As you've all come by to my house to pick up door prizes and handbooks and calendars, and it was great to see all of you. By this time next year, there will be a new chair, and hopefully that new chair will get to actually stand in front of you, something that I miss very much. And that new chair will be able to deliver a year-end message in person, actually face to face. But for now, I want to say thank you to all of you for sticking with us through this transition. I am very glad that you are still here. A big thank you to all who pitched in to help find new ways to keep the club going, and the people who worked hard to make those innovative ideas a reality. And finally, as Matthew said, I want to echo, I want to wish you all well. I want to wish you all a safe and happy new year. I want to say that however you celebrate at this time of year, whatever holiday you recognize, whatever customs you observe, that I hope it is with peace and health for you and your loved ones. And of course, as I always do, since I get to be up at the front of the room so often each year, I would like to close with the words of Clement C. Moore, who finished the final lines of his famous poem with words that seem particularly well suited to us lovers of the starry sky. And he, of course, said, Merry Christmas to all, and to all a good night. So, and good night to all of you, and thank you, and stick around and chat and visit. So, and we'll see you next month.